This video is brought to you by Chalk. Use code TPSA 10% off to get a discount.
So hello everyone, welcome to our second last talk of the semester. Today we have Professor Sint, who will talk to us about measuring the strong nuclear force. So yeah, thank you everybody for showing up, and we'll get started.
Okay, thank you very much for the invitation and the introduction. So I want to tell you something about basically my line of research, and has to do with a strong nuclear force. So let's get started. It's just an outline of my talk. I want to tell you a bit about quantum chromodynamics in everyday life. Then I will get to Lattice QCD and numerical simulations. And the problem that you have in a numerical approach is always that you have a limited range of scales that you can cover, that your resolution, that you can resolve. And so we encounter some large scale differences and have to basically be creative and solve that problem. So I will present a solution and then present a few results from the alpha collaboration. I'm a member of that alpha collaboration. There has been I think we have a history that goes back to the 90s, and there has been another alpha collaboration being created just some 10, 15 years ago, which is an experimental collaboration looking at anti-hydrogen, I think. And they didn't do due diligence and just didn't notice that this name was actually taken. So I'm a bit upset about that, as are my colleagues, but okay, that's how things are. Okay, so this is not the same alpha. We will distinguish the alpha, the fine structure constant, and the strong coupling constant later on. So let me get started on the QCD or quantum chromodynamics part of the standard model. So it's one of the pillars of the standard model, and it describes this. The standard model describes the strong and the weak nuclear interactions and electromagnetism. So there are three interactions. There's weak nuclear and electromagnetism, and then I'm talking about the strong interactions. And then there's gravity, but gravity is kind of put aside for all these microscopic physics studies. Not all of them. Some models exist where gravity plays a role, but that go beyond the standard model. The standard model is just about the known interactions except for gravity. So now QCD describes the strong interactions of quarks, antiquarks, and gluons, and it fits on Frank Wilczek's blackboard. Frank Wilczek is a Nobel Prize winner, got the Nobel Prize for Asymptotic Freedom. We will later talk about that. And this is the QCD Lagrangian, the Lagrangian density, really. You have seen Lagrangians in mechanics, I guess, in first year. And so this is a Lagrangian density. So if you integrate over 3 volume, you get a Lagrangian, a proper Lagrangian. And that's QCD. That looks fairly simple. That's it. And the 3 parameters here, maybe we can use the mouse for pointing. So the 3 parameters are basically here, the MJ. J goes over the different types of quarks that there are, different flavors, as we say. And I have listed them here. So there's up, down, strange, charm, bottom, and top quarks. Okay, so that's the J sum here. And then there is G, which is here, in front of this term, which looks like a Maxwell Lagrangian. If you're in third year, you may have seen the Maxwell Lagrangian. That's a generalization of it. And here you see the field strength tensor. The first part, as I said, looks like the Maxwell part in relativistic notation, so containing the E and B field. And then you have a part which is there only because QCD is based on a non-abelian group SU3 and not on U1, which is a group for QED, the gauge group. Okay. If that is Chinese to you yet, then don't worry. I will go slowly, and then at the end it will get a bit more close to the research. So quarks and gluons. so quarks carry a color charge, and this can, unlike electric charge, cannot just be plus and minus. It can have 3 different states, and they have been basically likened to the colors. So color is an analogy that people use, and say you have a red, green, and blue charge for each quark or antiquark. And the strong interaction between quarks are transmitted by gluons. So gluons basically replace the photons of a QED, of quantum electrodynamics. And so you have the same type of diagrams. If you have a quark scattering off another quark, you have an exchange of gluon. So that is a modern description in quantum field theory terms of an interaction. You have a force carrier, and you exchange these gluons, in this case, to transmit the force. And if that was a photon exchange between electric charges, that would be exactly the same diagram. Instead of the coupling G, you would have the electric charge of the charged particle. And this diagram would lead to the Coulomb law. Okay, so if you look at the interaction that is transmitted, you get the Coulomb law, the 1/distance squared force that you all know. Now, what is the main difference to photons is that we also have gluons that self-interact. So there are these self-interactions, and they go back. If you go to the Lagrangian here, you see these additional terms in the field strength tensor. They are quadratic in the fields, not linear, and they lead, if you put them here, if you square this, in this term here, you will have terms with 3 and 4 A fields, and each A field is a gluon field. So you have vertices which couple 3 gluons together or 4 gluons together. And that makes the theory very nonlinear. And in particular, the superposition principle that you know from electrodynamics, so that doesn't work in QCD. So you have a nonlinear behavior. Okay. So quark confinement. So these additional interactions are basically responsible for the fact that we have never observed quarks or gluons in isolation. So they're never observed as free particles. They're always confined in bound states, which are generically called hadrons. And examples of this are protons or neutrons or pions or pi mesons. And so protons and neutrons are what's known as baryons, examples for baryons, which are 3 quarks bound together. So 2 up and a down quark make a proton, and 2 down quarks and 1 up quark make a neutron. And then you have mesonic states like a pion, where you have an up and an anti-d quark. And the combinations are such that you can make states that have no color, or white. I mean, white combinations of 3. So if you combine the 3 fundamental colors, you get either white or black. And, so the confinement hypothesis is that you always have combinations, bound states, that mix the colors such that you have no net color for the bound state. Yeah. So here, for example, you would have color and anticolor in the pionic or mesonic state, and that mixes to no color or colorless state. Or you can mix 3 colors, like in baryonic, like in proton and neutron, and you get a state that is colorless. So quark confinement, yeah, so there's a qualitative picture. You can think of this if you take a meson-like bound state where you have quark, antiquark, and you try to separate those. Then you need so much force that the energy in the force field basically is enough to create a quark-antiquark pair out of the vacuum. And you get this. You get 2 bound states instead of 1. So instead of getting individual quark and antiquark, you get 2 mesonic-like states. Yeah, by this. So we can think of a bit. There's the analogy with a magnet where you try to isolate south and north pole by cutting the magnet, but what you really get are 2 magnets again, right? I mean, each has north and south pole, or plus or minus pole, whatever you want to call it. So that's the qualitative picture, and it's a semi-classical idea. In quantum field theory, this is, of course, more complicated, but it captures the essence of it. So the confinement hypothesis I already mentioned is that you always have white states that are the observable states in nature are the white combinations of quarks and gluons in all possible ways. And so then the question is, what is the status of quarks and gluons? I mean, in experiments. I mean, how do we even know about them? And so there is some history to that, which is quite interesting. So quarks were introduced I think in the 1950s, basically as a mathematical tool, as basically an ingredients to classify the observed particle zoo. People saw loads of particles. They were first observed in cosmic radiation, and then also in laboratories from the 1950s on. And there were dozens and then later hundreds of particle states observed, and it was called a particle zoo. And basically the same way that the periodic system of elements provided order to the different elements and atoms by having them classified by their electronic shell structure. In a very similar way, you can classify the bound states of quarks. At the time we didn't know about the quarks, but the quarks were invented basically to classify these hadronic states. And that was Gell-Mann and Zweig did that in the late 50s, early 60s. And so it was very successful, and there was even a prediction of so you have certain representations of the isospin SU2 or SU3 flavor symmetry group, and they come in unitary representations, and then you can identify the states that are in these representations of the symmetry group. And then there was some state missing. The omega meson was missing, and also the omega baryon later, I think. So they were basically predicted by this symmetry pattern and only later found in experiments. That was a big success. But there was no physical reality attached to these quarks yet until in the 1960s. There were experiments in late 60s in Stanford first, where people did inelastic scattering. I think neutrinos on protons or electrons on protons. Deep inelastic scattering means that you basically so elastic scattering means that you have the initial states, they stay the same, and you see the object only as a whole and not as but if you really are inelastic, you have high enough energy basically to resolve the inner structure of the particle. It's a bit like the continuation of the Rutherford experiment, where the gold foil, the gold atoms, basically you shoot these alpha particles, which are helium nuclei, on the gold foil, and they go through most of the time, and only occasionally they hit a point-like substructure, which are the gold atoms, gold nuclei, and then you get very large angles. And then from the angular pattern, you can deduce these point-like centers of diffusion of the scattering experiment. And very similarly, you can, at a much lower scale, I mean, the proton is something like 5-6 orders smaller than typical atoms. So at the atomic physics scales, you 10 to the minus 10 meters. 1 angstrom is the diameter of a hydrogen. So the diameter of a proton is 10 to the minus 15 meters, which is 1 Fermi or femtometer. And so that's a factor of 100,000 smaller. And if you have correspondingly higher energies, then you can resolve even the substructure of a proton. And that is what happened in the 1960s, late 60s. And then these substructures were later identified with the quarks. And then in the 70s, there was quantum chromodynamics was developed as a theory of quarks and gluons. And since then, we're struggling trying to extract quantitative predictions for physics from that theory. Okay, in particular, you would like to do experiments on quarks directly, and you can't, because you can't prepare an initial or a state that contains 3 quarks. So what does it even mean to talk about the coupling of the quarks to a gluon? I mean, how do you measure its strength. I mean, unlike in quantum electrodynamics, here if I have the example here of Thomson scattering. There you just have light basically incident on some charged particle. The charged particle will be excited by the electric field in the light and will emit in the Thomson limit at very low energies. It will just emit light in exactly the same wavelength in some other direction. So it will be a scattering of light on a free electric charge. And that is in this diagram, you have the incident light on some electron, say the electron then re-emits a photon and goes its way. And the photon has the same wavelength as the initial state, and that's the Thomson limit. And you can calculate it in classical electrodynamics, and the scattering, the cross-section, sigma Thomson, is given by 8 pi over 3, and then you have alpha over the electron mass squared. And alpha is the fine structure constant, E squared over 4 pi. It's known very precisely. E is 1 over 137 roughly. And you see that constant popping up everywhere in atomic physics or in quantum mechanics if you did that. Okay, so this, so this is very different in QCD. You cannot prepare a gluon incident on some free quark. And what does it even mean to talk about the strength of the coupling or even the mass of a particle that never exists as a free particle, unlike the electron. So that's the problems that we have to solve, and that I was alluding to by the title, Measuring the Strength of the Nuclear Force. Okay, so I have used here in this formula natural units. So just a note on units. Normally you would have the energy squared in relativistic physics. This is a relativistic relation. P squared C squared plus M squared C to the fourth. And that becomes in natural units where you set H bar and C to 1. Just E squared is P squared plus M squared. And so in that system of natural units, energy has the same unit as momentum, same as mass, same as 1 over length, and same as 1 over time. Okay, so that is just a very natural and convenient choice of units if you do particle physics. But of course, if you talk to other physicists or to anybody else, you ought to restore standard units at some point. But that can be usually it is very easy to do if you're a bit used to it. You just have to basically get back to the standard units by dimensional analysis. For example, the Thomson cross-section. A cross-section is always units of an area. So you need length squared. And you see that h bar over c is a length, and you just multiply h squared over c squared. And that is then your cross-section in standard units. Okay, and so that can always be done like that. Okay, good. I put a note that we do insist that pi is different from 1. Yeah. But apart from that, it's a very convenient system, and the danger is that you remember only the formula in natural units, and then if you have to teach in the first and second year, you tend to forget crucial factors. Okay, one has to be careful. Okay, so here I'm coming to then the property of QCD, which is called asymptotic freedom. And I've put a plot here with various experiments, which basically gives, so the fine structure constant, the equivalent of that in QCD is g squared over 4 pi. I said it's e squared over 4 pi natural units in QED. And also in QED, there are quantum effects which make that this is actually not a constant. It acquires by quantum effects, if you do quantum field theory and calculate quantum corrections, you will find that alpha, the fine structure constant, has a dependence on a scale, on a momentum scale. And the same happens for QCD. So here it will be, it depends on the scale. And this scale dependence can be measured approximately. We'll say in a moment how this is measured. And you see if you go up in scale to ever higher scales, you find that this is a decreasing function here. Yeah? So all these points with error bars are experimental measurements, say from tau decays, from jets at Hera. Hera was an accelerator in Hamburg, DESY in Hamburg. Heavy quarkonia. There's E plus E minus physics, so jets and shapes. That was done in CERN before LHC, and there was in the same tunnel there was an E plus E minus collider called LEP, Large Electron Positron Collider, and then various other experiments. Okay, and there is some value for alpha S extracted from these experiments, which is given here. And this is about at 90 GeV, MZ is 90 GeV is about here. So that is the value of 0.12 roughly, or 0.118. Okay, so how would you measure, for example, here in the jet physics measurement? So what you can do, say if you have E plus E minus collisions, like in the precursor of the LHC, E plus E minus, then you create, say, a highly energetic photon, virtual photon, and that decays into quark, antiquark in many cases. And then quarks, antiquarks, they will not stay free, antiquarks and quarks, but they will what's called hadronize. They will form, and the way you see that is basically you see very collimated jets back to back. For example, a two-jet event. This is an example of a two-jet event where you have very many hadronic particles like protons, neutrons, pi mesons, k mesons, whatever. Hundreds of particles, very collimated in a given direction and back to back the same. So two jets of hadronic particles. And so that would be this reaction here. And the fundamental reduction is just a creation of a QQ bar pair from E plus E minus, where the intermediate virtual photon is here not shown, okay, in this picture. And occasionally, you also create a third jet, so you have three jet events. And that can be understood basically as, so you have quark, antiquark pair creation, and then one of the quarks, the quark and the antiquark, they radiate off a gluon. And that, so you have basically the quark, antiquark, and the gluon, and then they hadronize in three jets in three different directions. And if you then just count the number of three-jet events over the number of two-jet events, then there is a relative coupling more in the numerator because there is this creation of gluon, which couples with a G, with a coupling constant G to the quark. And if you take the amplitude squared to get a measurement, that is G squared, which is proportional to alpha. So you get alpha, a measurement of alpha, or some idea of the size of alpha from just counting three-jet over two-jet events. And then the typical energy that you have in that reaction is basically the energy of the E plus E minus pair that you have. So this is very high energy. But you have this problem that you have to somehow, if you want to now quantify this, you have to deal with the hadronization process. That the quark that somehow transforms into a jet of hadrons. And there is what people call hadronization Monte Carlos. They model this process by looking at very many of those, and they have very good control over many things, but this is still a model. It's not fundamental QCD anymore. I mean, you have QCD plus a model for the hadronization, essentially. Okay? And you hope that this modeling effects are small and somehow under control. Okay, so then, okay, I'm not sure. How much time do I actually have? I didn't ask. So I can go for 1 hour, or is it too long? Yeah, okay. I shouldn't be more than that, yeah. So I don't want to keep it too long. So asymptotic freedom of QCD actually allows us to at least get a theoretical definition of what the coupling and so alpha and the masses of quarks, what they mean. And yeah, I will explain that in a little bit more. So I have said that there is these model assumptions in perturbative. So if you try to experimentally determine alpha from experiments like jet physics or similar, you always have in some form or other, you have some hadronization problem, or you have to there's some what people call quark-hadron duality in some rules. So there are very many different forms this can take, but you always have some discussion of that which you have to include and you have to model it. So if you look at the scale evolution at large Q in QCD, then you can actually you find that alpha depends on Q. This is the so-called beta function that defines that. It has a perturbative expansion, so perturbative in alpha. So you do a series expansion in alpha. And the first term is minus beta 0 alpha squared, where beta 0 is a positive coefficient. And that means that the coupling decreases for large energy scales mu, and this is basically reflected by this decrease here. Okay, and at large Q, this should become small, and therefore the coupling between quarks becomes smaller and smaller, and this is what is termed asymptotic freedom. So basically, if you have quarks that are very close together, very high energy means very small distances. And so if you have quarks that are very close together, they behave almost like free particles. Okay, so that is asymptotic freedom. And that's very unintuitive. People for a long time thought they had made mistakes in their calculations, a sign mistake. I mean, a good physicist does a couple of sign mistakes, always, pairwise. But you can never be sure. And there was actually a Nobel Prize for this sign. I mean, in 2004, there was a Nobel Prize given to Gross, Politzer, and Wilczek, whose blackboard you have seen before, for the discovery of asymptotic freedom. But of course, if you ask Samson, then he will tell you that was all discovered in Russia before. And yeah. Okay. So there is some interesting fact here. Beta 0 and beta 1, the first two coefficients in that expansion, they do not depend on the renormalization scheme. I mean, I throw this at you. The renormalization scheme is something you need once you do loop calculations in quantum field theory, which is some years away for most of you. Maybe it's you never get to there, because it's even in the senior sophister. I mean, the quantum field theory course barely gets to renormalization. I mean, that's advanced topic. But if you do these calculations, then you find that different schemes, which renormalization schemes, can be related perturbatively, and then you can define a beta function in each scheme. And what you find is that whatever you do, the beta 0 and beta 1 coefficients are the same in all schemes. So that's meant by universality. And so in some sense, the high energy asymptotic regime develops some universality. And this is basically what saves the day for the definition of the coupling and also for the definition of quark masses. Okay? So a natural question is then how to relate the hadronic regime at low energies, where you have all these bound states and the coupling is large, and you want to relate that hadronic regime to the high energy regime where you have almost free particles, and you have a huge difference in scales. Okay, so that's where Lattice QCD and numerical simulations come in. This was the logo of some conference in Lattice field theory, which took place in Florida. Okay, so Lattice QCD, what is it? So basically what we do is we have in QCD, in the continuum, we have the quark fields and the gluon fields. They are fields, which means they are functions of space and time. And so what we do here is we instead of taking continuous space-time, we replace it by a space-time lattice with spacing A and linear extent L. And since for us the lattice is not something fundamental like in crystallography, where you're interested in all kinds of nice lattices, body-centered cubic and whatnot, and you do nice symmetry groups, over those. We are not interested in the lattice per se. It's just a device to regularize the theory. Basically, you can't have wavelengths shorter than a couple of lattice spacings, and that cuts off the high momentum modes. So we use a finite volume. So then we sample the quark and gluon fields only at the lattice points. And that means that instead of having infinitely many degrees of freedom, if you have a finite volume with a lattice, this will be a finite number of degrees of freedom. For instance, we have a 3x3 unitary matrix, U mu of x, on each of the links of the edges of the lattice, so connecting two sides. And the quark fields and anti-quark fields, they live on the sides. And so a lattice gauge field configuration then, it's a bit like in statistical mechanics. You have an Ising model, for instance. You have an assignment of plus or minus on each side of the lattice. Yeah, so you have 2 degrees of freedom on each side of the lattice. If you have a 10 by 10 lattice in 2 dimensions, you have 100 points, and you have 2 to the 100 different configurations on the small lattice with just 2 states. I mean, this is enormous numbers. So here you have, say, a unitary matrix on each of the links, and you have quark and anti-quark fields on each of the sides. And then you do, like in statistical mechanics, you do expectation values. You integrate over all possible configurations of gluon and quark and anti-quark fields. And we do that in the Euclidean, where you have e to the minus the action. The action is the integral of the Lagrange density that we had. So this looks very much like statistical mechanics, and technically there are very many similarities. So you can think of this as a very peculiar system in statistical mechanics, where we compute expectation values. And all the physics information is buried in such expectation values. Yeah. Okay. So then what is S? S is the action of the gluons. That's the lattice version of this trace G squared, of this G squared term in the Lagrangian density that we had before. And then you have basically an action for the fermions, which is always bilinear in the fields. So this is a psi and psi bar with some matrix in between, which is local. So this is the Dirac operator for those who know a little bit more. Dirac operator transcribed to the lattice, but you can write it as a matrix kernel of that operator, and then you have this double sum here with a matrix kernel. And this is a generalized Gaussian integral. Okay, the Gaussian integral is integral dx e to the minus lambda x squared. So you write dx, and you have, say, e to the minus lambda x squared, where lambda is some positive constant, and you know that this is square root of pi over lambda. Yeah? And then if you generalize this to a matrix integral, then you can diagonalize the matrix if it's non-negative, or it should be actually it should be positive matrix. And if it's diagonalizable, then it's basically producing a bunch of such factors for each eigenvalue, and you get basically pi to the n half over the determinant of that matrix, or square root of the determinant. If you do the same for fermion fields are Grassmann, which means they're anti-commuting variables, and you can define integration over Grassmann algebra, Grassmann variables, but they have you just require linearity and very generic properties, and then you find that you don't, instead of getting 1 over determinant, you get the determinant itself. So that's a famous fermion determinant. You may have heard of fermion determinants before. They cause all kinds of trouble in all kinds of fields of physics. So if you carry out the Gaussian integral, so in this integral here, you have an integral over psi and psi bar, and you can do this integral exactly. Yeah, and then you get an effective action. So you still have the integral over the gluon fields, which is this u variables left, you have an effective action, which is the gluon action, and then you have the determinant of m, basically, that you exponentiate, or you have a log here. And you have O, the observable. If it contains fermion fields, it has to be become a function of the gluon fields only. So this O tilde is the effective description of the observable after integration over all the fermion fields. And so that is the starting point then for a simulation, for a numerical simulation. So what you want to do is then you want to produce a sequence of gauge field configurations, where gauge field configurations is an assignment of a gauge link to each link in the lattice. And you invent a process that moves in the space, in the probability space over these gauge configurations, and will have as a fixed point in the evolution, will have the desired distribution here, e to the minus s effective, as a fixed point distribution. So you basically invent a process, you wait until it's thermalized, that's the common parlance, and that which means that you arrived in the fixed point distribution, and then you start sampling configurations, and then you want to average over your observable over these configurations, and you want to calculate an error estimate of your estimate. So this is a way to estimate expectation values in this peculiar statistical mechanics system that is our Euclidean time quantum field theory on the lattice. So you see the expectation value is estimated as just an average over all these values of the observable in the representative gauge field ensemble. And then we have an error that's epsilon, and one can show that the error goes down like 1 over square root of n, where n is the number of the statistic that I have. Okay. So let's do an example. Let's compute the mass of a pi meson. So a charged pion is basically a composite field of a quark and an antiquark, so UD bar, I told you before. And it's a pseudoscalar under Lorentz transformations, a parity transformation is a pseudoscalar, and a quark bilinear with gamma 5 in the middle is a pseudoscalar field. That's a pi plus meson, and if you take the Hermitian conjugate, you get the pi minus with U bar d. And then the propagator, the space-time propagation of that pion field from x to y, or from y to x here, is given by this expectation value, by this 2-point function, depending on 2 points, x and y. So you can interpret this as a pi meson being created at space-time point y, propagating in Euclidean time to space-time point x, and being annihilated there. So that's this function g, capital G of x minus y. So it depends only on the difference, because we assume translation invariance in all directions. So we have typically periodic boundary conditions, so that we're on a hypertorus topology. So in all directions, also in time, we have periodic boundary conditions. So then, when you then look at the observable that you get for this operator now depends on the fermion fields. And if you integrate now by cross-band integration the psi and psi bar fields, all of them, if you integrate over U and D bar, they are contained in this psi and psi bar. And then you get, this is the O tilde observable, that you get this trace of these matrices, where M inverse is the inverse of the Dirac operator, or the kernel here in this action. Okay, so, and this is a huge matrix. M is a huge matrix, and you need to invert that matrix to evaluate this observable. Okay, so to invert this matrix, what you have to do is to solve linear systems of this type. And the fermion matrix M is a sparse matrix, which means it has lots of zeros. This is because the action is local. It's an integral over local Lagrangian density, and therefore, if you look at M as a function of x minus x and y, it will rapidly decay or even be zero after a short distance. So but it's of rank 12, which is 3 colors times 4 Dirac spinor indices. That's 12. 12, and then you have it's on each lattice points. If you have an L to the 4 lattice, L over A to the 4 lattice, then it's the 4th power of that. So if you have a 48 in each direction lattice, this is 12 times 48 to the 4, which is 63 million and something. So that's the size of your matrix. So you never store that matrix. I wouldn't recommend storing it. What you always do is you have iterative algorithms where a vector is mapped to a m times the vector. So you only store ever the vector, but the vectors have this size too. Yeah, that has to fit in your memory of your computer. Okay, so then the Pion mass you will obtain from basically from the exponential fall off as you look at the propagator as a function of the distance in time. So let's say we sum over all the spatial indices. X here means the spatial indices, and we have a function of that's the 0 direction, which is the Euclidean time direction. And then we want to see how this behaves asymptotically as we pull the two operators apart. So x0 becomes large, and then the dominant term will be e to the minus x0 times the Pion mass. And then there will be exponential corrections, exponentially small, which will go with the next state with the same quantum numbers. That the next excited states that sets the distance delta, capital delta, above the Pion mass. Okay, that will be the correction here. Okay, that in nature they would expect a 3 Pion state for that. And so the threshold for 3 Pions would be, and then you have a cut. Well, on the lattice you never have cuts because you have discrete momenta. Because in finite volume, I should say, not on lattice. In finite volume, your momenta are always quantized. So your spectrum, even if a continuous spectrum for continuous momenta, becomes discretized because your momenta are quantized. Okay, so in practice, how does one extract an estimate for this Pion mass? You define what's called an effective mass. So we take the ratio of this propagator at subsequent lattice time slices, and the logarithm of it is just an estimate of AM pi up to exponentially small corrections, and you look for a plateau then in x0. So here's an example. You see the effective mass as a function of x0, and you look for the range where it plateaus. And then the plateau value here, say from here where this is safe, you average over the plateau range, and that gives you an estimate of A times the M effective, which is then the Pion mass in lattice units for the chosen quark masses that you have, which need not be the physical ones. Okay, so that's actually one thing we can on the computer we can actually dial our quark masses. It's not that they are fixed like in nature, and that's actually interesting. You can get a lot of insight by varying the quark masses. Okay, so that is an example just to give you an idea what a simulation means really, right? And it means usually that you need parallel computing, big computers, and you apply for resources on computer centers to get computer time for a given project. So there's peer review for that, and so you submit an application, and there is some peer review, and then you get time on some European machine if you have exhausted your local resources in national resources. Okay, so now what we want really is a controlled connection between the perturbative and the hadronic regimes of QCD. So we want to, in order to determine basically alpha S and the quark masses from hadronic input at low energies, and we want to get to this universal high energy regime where we can define what a mass and what a coupling means, really. Okay, and a requirement is, of course, that if you do hadronic physics, that a pion must fit comfortably in the box. Otherwise, you distort the physics by the finite volume. Right, so a pion is the lightest particle typically, so that's the strongest constraint on the volume. And so what you want is that the Compton wavelength is 1 over m pi in natural units. This is length, is small compared to the extent L. And if not, then, so what you always have is basically that the pion in a periodic box will interact with its copy that's one period further apart. So this is basically pion polarization around the world, if you like, in the various directions. And these effects are exponentially small in the pion mass, because as long as the pion has some mass, it will be exponentially damped in all directions. Okay, so there is some hope that this is not too bad. But if it's too small the volume, then you will see effects like this. I'm not sure if you have seen that before. That's Japanese square watermelon. So it's Japanese love fruit for gifts, and they let them grow into boxes. And it's also a practical idea. I mean, you can pack them very densely. I guess Stefan Hutzler will have trouble to match that with spherical ones. Okay. So the problem of large scale differences, we must also make sure that we reach the perturbative regime, that the scale must be much larger than, say, typical hadron mass, like the proton. But then the lattice cutoff should still be much larger, because we don't want to study the physics of the lattice cutoff in lattice QCD. That's not interesting. There's no new physics to be discovered there. It's just an artifact of the lattice. So we want to have mu, this large scale, still much smaller than 1 over a. And if you put these much larger than and much smaller than all together, then you find a string that a has to be very much less than L. And if you take it seriously, then you need 1,000 points in each direction, not just 48 that I had given as an example before. And typical lattices today are, I mean, this could be updated maybe. I mean, people go to 100 points, but these are the largest, say maybe 128, or people try this, but you need a range of lattice sizes, and you need a range of lattice spacings as well in order to take the limit where a goes to 0 in the end. In the end, you want to take the continuum limit where a goes to 0. Okay, so that's implicit always. Okay, so this is just an illustration that very different scales cannot be resolved on a single system where you have, unless you put enormous size lattices. So what is the intelligent approach is to break it up in smaller steps, and that has been done in the 90s. At least the principles of that have been discussed in the 90s, and since then we're realizing this type of approach. So what you do is you define the coupling and also quark masses as so renormalized coupling that runs with the volume. So you use the volume to set the scale, essentially. So L is a length scale, so 1 over L is an energy scale, so that is your momentum scale or mu scale on which the coupling will depend. And then you just study how the coupling changes as you change the volume. Okay, so and particularly what you do is you look at the step scaling function. So you do scale changes by factor of 2, so which means you double the volume. Okay, and that is very easy to do on the lattice. You take a lattice 4 to the 4, and then you take a lattice 8 to the 4. Then you take 6 to the 4 and 12 to the 4, and so on. You pairs of lattices, and and then you define. So in the continuum would have a function little sigma here of u, which is the coupling constant at twice the box size, with u being the coupling at the box size, the original box size. So sigma of u basically tells you, given the coupling at L, what is the coupling at twice L? Yeah, and if you and you can get this function. This is a continuum limit of lattice approximants where you do what I just said: 4 and 8 and 6 and 12 and 8 and 16 and 12 and 24, and you get lattice approximants, capital sigma here, which depend on the resolution, and then you take the limit and you get this continuum function, which tells you how does my coupling vary if I change the scale by factor 2. And then you generate data for various values of u in some range between a minimal box size and a maximal box size, L min and L max. And in that range where you have values, you can iterate the procedure. You can define your initial point as the coupling in the smallest box size you have, and then you read recursively uk is sigma of uk minus 1, and so on, for k equals 1, 2, 3, and so on. And you get to g bar squared at 2 to the k times L min. And if you have 7 or 8 steps done, you have an order 100 scale difference covered. And actually, we can easily do a factor 1000. 10 steps is 1000. 2 to the 10 is 1024. Okay, and so what you then need to do is to, in the maximal box size, which is now at low energies, you compute a hadronic quantity, and there you don't have a large scale difference now. You have a large box size, and you have hadronic quantities that you can compute at the same volume. And you compute, for example, f pi times L max here. F pi is the decay rate of the pion, so lifetime of a pion decay into muon and antineutrino. And so you from that measurement of lifetime you get the decay rate, and that's a very well measured quantity that you can also compute on the lattice. Okay, so here's just an illustration of what I just said: 4 and 8, 6 and 12, and so on. Okay, I have said that before. So and then you have data for different u values. This is the continuum extrapolation. So this is the lattice. Each of the data points is a lattice approximant of this step scaling function, and you have different lattice sizes as you go from right to left, and different u values as you go from set of points to the next set of points. So which means that you have in the range where u varies between say 0.998 and 3.3, that's your interval in which you construct this function by going to the continuum limit of these points, and then you see these points are your data, and then you interpolate this data to have a function, sigma, little sigma of u, which you can use recursively to step up the energy scale. And then you get this type of, so this is the function sigma of u over u, the data that you produce, and then you use that to actually look at the running of the coupling itself. So the step scaling function gives you from, if you start at this smallest coupling, from this point to this point is one step in factor 2. So factor 2 down in energy or larger in box size. Yeah, and so it's each of these points are separated by a factor 2, and the line is basically integrating backwards using the perturbative beta function. And you see there is, at the lowest energy scales, you start significantly deviating from the perturbative beta function, which is only supposed to be very good at high energies. So here is some more push towards even lower energies for the pure gauge theory in this case, and this is 2-flavor QCD. Okay, yeah, I see there is not so much time left, but I think I'm getting there. So here is the so-called lambda parameter of QCD. This is this. So the beta function I've explained. The beta function starts. Yeah. Okay. Starts with perturbatively with the terms order g cubed. So if you have 1 over the beta function, and you want to integrate from 0, this is singular, and you have to subtract the asymptotic terms to make this square bracket is a regular function then for x going to 0, which is the coupling. And so this lambda is basically, you can trade the coupling for the lambda parameter, essentially, as a fundamental quantity that you want to determine. And lambda is a scale, and it's a solution of the renormalization group equation, which is independent of mu. So lambda is, you see mu here, and this is g bar of mu, and this is g bar of mu here. So mu is the argument of g bar on the right-hand side. But this particular combination, you can show that this does not depend on mu. So you can evaluate it at any value of mu. And so you can evaluate it, if you evaluate at very large values of mu, then you can actually use perturbative information on the beta function and just evaluate this integral, because you integrate from infinite mu, which is 0 for asymptotic freedom, you have 0 coupling at at infinite energy, to a perturbative regime where you can still use a perturbation theory for the beta function. And so you can, if L min is a perturbative scale, you can get lambda L min, and by computing this right-hand side at the scale set by the minimal box size. And the mistake that you make, if you evaluate this integral here in perturbation theory, you see that if you know the 3-loop beta function, B2 is a 3-loop term in the beta function, then you get this integral to order g squared, and then the error is order g to the 4th. And if the coupling is small enough, then you can maybe neglect g to the 4th. Yeah, and this appears in the exponent here. E to the something g to the 4th is your error. Okay, and then since you know that L max is a factor of 2, a power of 2 away from L min, you know also that if you can do that determination, you know also what L max times lambda is, and then you need L max in units of f pi to know what lambda is in physical units. So that's the procedure. So in practice, what you do is you define a scale by saying that the coupling has a certain value. That defines a scale, L max. So this largest coupling that we reach, and then you have a box size implicitly defined. So you don't know how much is it in femtometer. Now or in inverse MEV. So if you follow that for different size lattices, always tuning to this value, this defines a sequence of values of lattice sizes as a function of the bare coupling. And so you have this ratio as a function of bare coupling. And now what you need to be able to do is to evaluate the Pion decay in a large volume at the same values of the bare coupling, which means essentially the same value of the lattice spacing. And if you have both of them, if you have a f pi, so f pi in lattice units as a function of the bare coupling, times the maximal box size over a in lattice units at the same values of the bare coupling, then the continuum expression for that is when the bare coupling goes to 0. Yeah? And then you get lambda in units of f pi, and then you take f pi from experiment, you know that it's 132 MeV, and then you know your lambda parameter in MeV. So that's essentially what you're trying to do. So I just present now some results. So we have the 3-flavor lambda parameter for 3-flavor QCD has been determined in this way essentially, and we get this result in MEV. So that's a fundamental parameter of 3-flavor QCD. And you can then look at the running of the coupling in 3-flavor QCD, and this green and purple data is real data. This is what we extract from our simulation. We have used 2 different definitions of the coupling here and match between them non-perturbatively because they have different properties at low and high energies, and we have to combine the two. For comparison, these red curves are the beta functions for, the running coupling for the MS bar scheme, which is the scheme where we know the beta function up to 5-loop order. So this is a major feat, a major achievement. This has been calculated to 5-loop order. And you see it at low energies behaves very different, but at high energies you see everything behaves eventually similarly. And there's this universality I alluded to. Now, but the reference value for phenomenology for experiments is really alpha S at the Z boson mass scale. Z bosons are quite heavy. They're about 90 times or 100 times the mass of a proton. So 91.2 GeV, roughly. And this means that we have lambda in the free flavor theory, and we need to get energies that are above the charm and the bottom threshold. So charm quarks are about 1.28 GeV. I didn't tell you what the mass definition is, so it can be vague here, but so basically 1.23 GeV and 4.2 GeV for the bottom mass, and then the top quark is 176 GeV, I think. So that's far out. By the way, nobody understands this hierarchy of masses in the standard model. The standard model these are 3 parameters, and there's no real understanding why there should be such a hierarchy, or for neutrino masses. So these are unsolved questions in the standard model. But if you're at this energy, you need to use active charm and bottom quarks, which means that the evolution of the coupling has to cross the charm and bottom threshold, but that can be done very precisely in perturbation theory. It has been tested. And therefore, you can then, if you have the free flavor lambda parameter, you can predict what the coupling is at all scales. And we get basically from our result that I described here, this is this result here with an error on the coupling of 0.7%. This was the result in 2017 already, and we have since used different methods, which I didn't have time to explain. But so here is a compilation of so this FLAC 2024 is flavor averaging, flavor lattice averaging group. It's an initiative of people from collaborations working in Lattice QCD worldwide. Some 25 people, and there are different working groups for the different quantities that are determined. And I actually, I'm the coordinator for the Lattice, for the alpha S working group. And so this is the latest plot that we produced. And so you see below here, there is the experimental or phenomenological determinations that you have seen in the previous plot I've shown you. And you see, for example, E plus E minus jets and shapes, you have these, this type of error, and then they produce an average of those. On the lattice, we do there are very many different, you can actually do very similar things. That's not the lattice determination. I mean, you can use, in some cases, like tau decays, also, you can use the same quantities that people use in phenomenology. You can also study this using lattice. And then you're hitting the same problems of having to discuss non-perturbative effects at low energies, which are, so you're not in the regime at high energies where you really can, with confidence, do perturbation theory, and all kinds of modeling goes on. So this is actually the case for most of these lattice determinations, except step scaling. So this result is basically what I have explained to you, this result. Then there is a decoupling result that's also done by us in the alpha collaboration, which has a similar error, and it is basically a non-perturbative connection between 3-flavor QCD and 0-flavor QCD by basically ramping up the mass of a triplet of quarks, so a fictitious triplet, ever heavier, and then the effective theory is 0-flavor QCD, or the pure gauge theory. And then the step scaling is still done, but in the 0-flavor theory, where it can be done much more precisely. So that is meant by decoupling. It would be decoupling 3 quarks and then make a controlled connection between 3-flavor QCD and the pure gauge theory, and use advanced techniques in the pure gauge theory, which are not available for the full QCD theory. So that's the decoupling result, and then one can actually basically average these two. They are pretty independent, and then one gets what is here the Flagg estimate. And the Flagg estimate, basically, we are careful not to average over all these numbers, because we want to keep an error that is statistics dominated. You would get a smaller error if you did the average, but we take as a proxy basically the step scaling and decoupling combined errors, because they are still dominated by statistics. And if you have a statistics dominated error, then you know what's in the tails of your distribution. I mean, that's a normal distribution. You know 68% of time you should be within one error bar, and 95% within two error bars. And if you have systematic errors, there's no way to tell what's in the tails, how much is in the tails. You can't give confidence intervals. And so therefore the emphasis is on getting small errors, but still statistics dominated. Yeah, that's the challenge. Many people come up with small errors, but then you get 5 sigma effects, you don't know what it means. Is that new physics, or is it just a problem of your calculation? Okay, so that's actually, there's a history. In the PDG, the particle data group, they have produced errors that were much smaller 10 years ago than they are now. And because they noticed there is a problem. And then the errors increased again. So this is a clear sign of systematic or theory error dominated results, where people just underestimate the systematic effects. Okay, so you see that actually the lattice determination is in much better shape than the phenomenological ones, and that's because we completely bypass the problem of hadronization effects. I mean, we directly compute the proton mass or the pion mass, as I've explained, and then this is not an issue for us. So we get very precisely measured low energy quantities as input, which determine then our coupling, or our lambda parameter, or the coupling at high energies. So we are trying to convince our colleagues in experiment at CERN and elsewhere in the PDG. I think they're already on board, more or less, to use a precise lattice determination of alpha to understand some of these QCD effects in collider physics, of the hadronization effects and the parton distribution function. The initial state in the proton-proton collision is very complicated. You need to basically you are very deeply inelastic, and so what really happens is quark-quark or quark-antiquark or quark-gluon parton-parton collisions happening. That's a fundamental reaction in a collider. And so what you need to know in order to know your initial state is what fraction of the momentum of a proton is taken by a quark or an antiquark inside the proton. And these are so-called parton distribution functions. And they're usually fitted to a lot of data, including alpha S. And alpha S is everywhere. And they could, for example, use alpha S as an input, very precisely determined from lattice calculations, and then see what are the problems that we have in certain corners of the parameter space for the parton distribution functions, and then hopefully get better handle on some of the QCD effects at these collider experiments. With that note, I would just like to thank you. Apologies for going over time, and if you have questions, please fire away.
Any questions?
From a phenomenological point of view, I've been assured that taking a large n limit is meant to help simplify calculations immensely. And I noticed that you've also been messing around with NF not being 3, like it is normally. I suppose, where does the utility in making that number of flavors a free parameter appear in lattice calculations?
Well, I mean, you're right. I mean, there's NF. We just had NF change, so we still have an SU3 gauge theory, and yeah. So whenever you change NF or N, you change the theory. So you have complete. So it's not clear what 1 over n expansion really means until you say how you match the theories at different n. Yeah. For NF, there is a bit, there is what is called decoupling. So it depends on the mass of the particle. If you go up with the mass of the quark, and we go up with the 3 quark masses at the same time in this decoupling project, then at some point, so you can say there's an effective theory description of that heavy mass QCD, which is a description without these quarks, essentially, up to effects we can calculate, which are of order 1 over the mass squared. Okay, so we can compute the corrections to it, and that's what we actually do, and we go to the limit of infinite mass, basically based on a sequence of very heavy masses up to 10 GeV. Yeah, but you have to really, yeah. Okay, so that's a dynamical question in this case, because it depends on what energy your experiment is at. So if it's at low energy compared to those masses, then you have a matching to the effective theory up to this 1 over m squared effects, which can be calculated. If you change the number of colors, you have a completely different theory, and you can formulate some matching conditions, say some couplings that stay the same, and then you see how other quantities are basically behaving as functions of 1 over n. But until you do that, say in the massless, say in pure gauge theory, you only have a single parameter, which is the coupling, the bare coupling. So as long as you give a prescription on how to match the coupling between different number of colors, you then have a well-defined question as to how a certain quantity behaves as a function of n or 1 over n. Okay, and that can be interesting. And because I mean, many of the exact results that people derive in gauge theories assume large n, infinite n essentially. And in infinite n, many things get very much simpler. For example, in the Feynman diagrams, all the diagrams that cannot be drawn in the plane, basically because you have lines crossing over and in the diagram, all those diagrams basically are eliminated in the large n limit. So you get only a subset of diagrams that contribute. In some cases, you have also situations where many of these series expansions that we have in the coupling, in the coupling, the expansion is not a Taylor series, it's what's called an asymptotic expansion with a radius of convergence which is 0. Okay, so that at first sounds a bit puzzling, but this is still useful. And there's a whole field of mathematics developed around it. But if you go to the large n limit, in some cases, this radius of convergence is finite all of a sudden. So it's a completely different situation. And yeah, I don't want to minimize these achievements at large n, but in practice, they give some qualitative insight sometimes as to the relative importance of diagrams in phenomenology. But beyond that, it's nice theoretical results that have not so much impact on phenomenology so far. Maybe there's a breakthrough in 5 years or 20 years. Anytime. Would be nice. But, I mean, this is the best we can do at the moment to get really quantitative results. Anybody else? Yeah.
Okay. 2 things for you guys. Towards the beginning, there was a graph of the coupling with different measures for different events. One of them was the equal C minus jets and shapes. It was like next to next leading order plus res. What does the res mean?
Well, next to leading order. I would have to look it up. Sorry, I don't know what it refers to. So next to leading order is the order in alpha S that you expand the perturbation theory. And yeah, so no, I would have to guess, but I don't want to say something wrong. Would have to look it up. This is a fairly recent plot from the PDG, the Berlin Data Group. There's a long report on QCD, and there is a long chapter on alpha S determinations, which treats all these different categories and explains all the details. If you are interested, just go to their website and have a look. Okay.
I guess more of a philosophical thing. Do you think that the mathematical illegalities that stem from the Borel summation or all the weird infinities and stuff that pop up pose sort of a limit on how accurate the standard model could be? Or do you think that this is sort of that we're okay to just sweep these things under the rug?
To treat what?
To just sweep these things under the rug, like.
They're not swept under the rug. No, we are not. Yeah, okay. There is a lot of. People have tried to resum asymptotic series, and then there is this Borel transform that you were alluding to, which is one way to do that, but it does not apply to most of these series because there are singularities in the complex plane that prevent you from doing that, and then people invent all kinds of other things so it becomes a whole swamp, I would say, and the real reason for that is really that you are at too low energies where you cannot really do perturbation theory properly. So people basically are forced to do something like that, or think they are forced to do some phenomenology and discuss these contributions because they are at very low energies where they cannot exclude certain effects, and the perturbation theory, even if you have for loop results, if you are too low energies, they don't capture the essence of the observable. Yeah, so the way out is to just go to high energies, and so this is possible. There is a whole field called resurgence, which tries to so the perturbation theory is basically if you have a path integral and you have the minima, the absolute minimum of the action, and then you have secondary minima and many. So nobody knows exactly how many and how to classify them. So instanton configurations correspond to certain secondary minima, but there are maybe many more things, and it's so when you do perturbation theory, you basically do a saddle point approximation to the integral and expand around the minimum. And while the total integral has a well-defined meaning, you neglect exponentially small corrections from when you do the saddle point expansion. And it's these exponentially small terms, basically, that are not small if you're at low energies in this case, which ruin the perturbation theory that you have. And but in resurgence, there are attempts to basically find some way of reconstructing the full integral from the structure of these minima, and that's a very hot topic. Yeah, so there is lots of things are ongoing there, and there might be a breakthrough at some point.